Alright, welcome to our discussion on polyatomic nomenclature. What is polyatomic? I think that we talked about this back in the ions section when we were learning about chemical bonding for Lewis structures, but we can review it again here. Poly means many, okay, and for us in this course, many is going to mean more than two. And the reason for that is because if there are two atoms in a molecule, it's binary. So any more than two, we're going to consider it polyatomic. Now here, this is a bit of a misnomer where it says atomic. Normally, we would think atoms, but what we're actually going to call that are elements. Okay, so it's talking about how many different kinds of elements we have in our molecule or our compound. Okay, so there are three types of situations for polyatomic compounds, just like there were three types of situations for binary compounds. The first situation we're going to talk about is the first element being a hydrogen. Again, that means it's an acid. And remember, I told you back in the binary video that this was the only rule that has no exception. If the compound starts with a hydrogen, it's an acid no matter what. Okay? So the formula, the general formula for a polyatomic acid is this. HX, and that X represents some subscript, some number that we don't know yet. Y in the middle. And then O, that stands for oxygen. So H is hydrogen because they start with hydrogens if they're acids. Y is going to be a nonmetal. So something like carbon, nitrogen, sulfur, those things that are on the right-hand side of the stair-step line. And then some number of oxygens. Okay? So here's the rule on how to name a polyatomic acid. You're going to say the stem of the nonmetal. Okay, now this is different from binary acids. In a binary acid, we said hydro first, but in a polyatomic acid, we say the stem of the nonmetal. So that's this thing right here in the middle. All right. We will include an appropriate prefix or suffix and then the word acid. Okay, let's talk about what these words right here are, just in case you don't know. Prefix means to come before, and suffix means to come after. So my name is Mr. Leatherwood, so the prefix of my name is going to be Mr. If I were a doctor, then I would be called Dr. Leatherwood, and doctor would be the prefix, and MD might be the suffix, meaning that I'm a medical doctor. Okay, or maybe you are I don't know, Harry Potter Jr., and Jr. would be the suffix. Okay, so pre comes before and the suffix comes after. All right, now what are we talking about when we say that prefix or suffix? We're going to use what I call the any-outie rule to help us figure out what the prefix and suffix are going to be. And here's how we do that. The number of oxygens in our formula. So here we have X, some number of oxygens. Those number of oxygens depend on whatever the nonmetal is. Okay, so whatever nonmetal is right here will determine how many oxygens have to be attached to it. That can go back to our Lewis structures, our bonding. This nonmetal is a specific element, and that element will have a specific number of valence electrons that are able to bond with something else. So if there are 4 openings, then there will be 4 oxygens. If there's 3 openings, then there will be 3 oxygens, and so on and so forth. Okay? And then that's going to create what we call an ic acid formula. So in other cases that we've already gone through, an ending might be ic or us, and that's going to be the same thing here for this acid. We're trying to figure out what the ic acid is. So here's what we're going to do. I want you to get your periodic table out, and then over in the P block, that's where we're focusing right here, you're going to put a 3 next to the boron, and you're going to put a 4 next to the aluminum, which is what goes right here. Okay, now these are what I call the outies because they're on the outside perimeter, and these are the innies because they're on the inside of the outies. Okay, now if a polyatomic formula varies on these numbers of oxygens here, then we're going to use these rules in just a second. But what I'm telling you all is that all of these elements that are outies require 3 oxygens to have an ic acid ending. All of these elements require 4 oxygens to have an ic acid ending. Okay? Now, let's take a look at your flow chart and see it there. Okay, we're on the polyatomic side of your flow chart. We're over here where the first element is hydrogen, and here's the rule. Stem of second element, then the prefix or suffix according to the any-outie rule, and then end with acid. Okay, so right here is the any-outie rule, okay? And what we're doing is coming up with the polyatomic anion name, okay? Remember that all of our formulas, all of our compounds have a cation part and an anion part, okay? So here we have hydrogen plus our polyatomic anion. That means that this is an acid because it starts with hydrogen. Okay, so if it has the number of oxygens that it's supposed to according to the any-outie rule, then the ending gets to be ic. If it has 1 less oxygen than the any-outie rule, the ending changes to us. If it has 2 less oxygens than the any-outie rule, then you have a prefix of hypo, and then you have us as your suffix. And if it has 1 more oxygen than the any-outie rule calls for, you have a prefix of per, and your suffix goes back to ic. Okay? So let's just take a look at a few example questions here. Okay? We want to name these. Obviously, these are polyatomic because there's more than 2 different kinds of elements. We have 3 here, and it follows that general pattern. There's the H, then we have the nonmetal, and then we have oxygen. Okay? Now, sulfur is the nonmetal. Here's that rule again. We need to say the stem of the second element. Remember I told you once before, when sulfur and carbon are in an acid, they say their full name, not the stem. They say their full name. So we're going to say sulfur, and then we need to decide what the ending is going to be. And so we're going to look at the any-outie rule to help us. Sulfur is an any, which means it needs 4 oxygens to end with ic acid. And you see here that this does have 4 oxygens, which means that we simply end with ic acid. Okay, so this is different than hydrosulfuric acid. That was binary. This is polyatomic, so it is just sulfuric acid. Okay, let's see if we can do this one down here. Again, it's polyatomic because it's got more than 2 elements. It is an acid because it begins with hydrogen, so we know we're going to finish off by saying acid like we did up here. And it's going to be named based off of the phosphorus. So we need the stem of phosphorus. Now remember, when phosphorus is in an acid, the stem is not phosp, it's phosphor. So we're going to write phosphor. Now we need to decide what the ending is going to be, and we need to look at the number of oxygens to help us. So let's use our any-outie rule. Phosphorus is an any, which means it wants 4 oxygens to end with ic acid. See here on your flow chart, if it has the number of oxygens that the any-outie rule says it's supposed to have, then it gets to end with ic. This has 4 oxygens just like the any-outie rule says it's supposed to have, so it's going to end with ic acid. Okay? Now I want you to see if you can do this one on your own. Okay, so hopefully you came up with chloric acid. It's polyatomic, so that means you're going to start with the stem of the second element, which is chlor. Then you use your any-outie rule to help you. Chlorine is an outie, which means it wants 3 oxygens to end with ic acid, and this has 3 oxygens. So we finish with ic acid. Okay, so far you know how to go from the formula to the name, and you know almost everything about that formula. You know why there's a hydrogen, because that indicates there's an acid. You know the sulfur is the nonmetal, and you know that it's an Ni, which means that there has to be 4 oxygens in order for this to be ic acid. You know all of that. The only thing you don't know is where that 2 came from. Why is there a 2 there? Same thing for this. Why is there a 3 here, and why is there a 1 there? There's a reason for that. The reason for that comes from the charge on the polyatomic anion. Okay? We're going to go back to crisscrossing and reducing. But you need to memorize this following saying right here, and I'll explain what it means after we've said it. Okay? Pos, Bos, and ASOs are -3. Sos, Cos, and Cros are -2. All the rest are -1, except ammonium, he's +1. Or if you prefer, she's +1. Okay, let's talk about what that means. Pos, Bos, and ASOs. That is phosphorus paired up with oxygen, boron paired up with oxygen, or arsenic paired up with oxygen. And then the next ones, Sos, Cos, and Cros, are sulfur paired up with oxygen, carbon paired up with oxygen, and chromium paired up with oxygen. And all the rest are -1. Now, these right here, I'm not sure that I've actually accounted for every single other possible polyatomic anion that we could have, but these are most of them, and most of the ones that we're going to run into anyways. So we have aluminum with oxygen, fluorine with oxygen, chlorine, bromine, iodine, silicon, nitrogen, and so on and so forth. So all of those are going to have a -1 charge, except for ammonium, he's +1. Now ammonium is NH4, if you'll remember. That was one of your exceptions that you had to memorize. So with this information, let's go back and take a look at those 3 practice questions and see if we can figure out where those numbers came from. Okay, so we're going to break these down into their cations and anions. So the hydrogen, since it was written first, is going to be the cation, and it has a charge of +1. Then we have what's called the polyatomic anion. That means an ion that's negatively charged that has more than one element in it. So that's the S and the O. And we know that Sos, Cos, and Cros are -2 charge. So when we crisscross, we bring this 2 down here. Now this 1 is understood, okay? And so it's out here somewhere, but we don't have to actually write that. Alright, let's see if we can do this one here. Again, the hydrogen is the cation, so it's got the +1 charge. And the polyatomic anion is the PO. Pos, Bos, and ASOs are -3. So when we crisscross, this 3 comes down here, and again, we don't have to write the 1. Alright, last one. Here, the hydrogen's the cation, +1. The ClO is the anion, and this is not a Po, Bo, or ASO, and it's not a So, Co, or Cro. That means that it's all the rest, so its charge is -1. So down here there's a 1, but we don't have to write it, and over here somewhere there's a 1 that we don't have to write. Remember, these numbers here are how many oxygens we have, and that's based on what nonmetal we have in there. It has nothing to do with the charge. Okay? Okay, now that we know that, we know everything about the formula, which means we are now able to go from the name to the formula. Let's see if we can get some practice doing that, okay? Here's the approach that we need to take. I see the word acid here, and I know that all acids begin with hydrogen, so we're going to write hydrogen. Then I notice that this does not start with the word hydro. Hydro is what we began binary acids with, and since it's not the first thing I see here, I know that this must be a polyatomic acid. And we start all polyatomic acids with the stem of the nonmetal. So since I see brome here, that must mean that the nonmetal is bromine. So we'll write bromine symbol. And then I need to include oxygen because in the general formula for a polyatomic acid, it always ends with oxygen. If I didn't do that, this would be a binary acid, and we already said it's not that. Alright, cool. Now I need to figure out how many oxygens I'm supposed to have here. Since this ends with ic acid, I can just go look at my any-outie rule and see how many oxygens I have to have on bromine for it to get to end with ic acid. Bromine is an outie, which means it needs 3 oxygens to end with ic acid. Now I just need to check my charges. Hydrogen is the cation, so it's going to have a +1 charge, and then my anion is going to be the BRO. So this is not a PO, BO, or ASO. It's not a SO, CO, or CRO. It's all the rest, which means it has to have a -1 charge. So +1 and -1 will cancel each other out, and so we don't have to write anything at all. Alright, let's try the next one. Okay, again, I see the word acid, so I know I need to start with hydrogen. Okay, again, there's no hydro in front, which means this has to be a polyatomic acid. So there's going to be a nonmetal and then an oxygen. The stem of the nonmetal here was sulfur, so I know there's going to be an S there. Now I need to figure out how many oxygens to give the sulfur. I notice that we have an OUS ending. Sulfur is an any and is supposed to have 4 oxygens to end with ic acid. Here's that OUS ending, and it says there's 1 less oxygen than the any-outie rule calls for. So instead of 4 oxygens, we're going to have 3. Now I need to check my charges. Hydrogen's the cation and has a +1 charge. Then our anion is this SO. So we remember from our saying that SOs, COs, and CROs are -2. That means we need to bring a 2 charge down here in between the H and the S. Okay, so now why don't you try doing 3 and 4 on your own. Okay, so here's what we come up with. Acid means that it has to start with hydrogen. Nitro is telling me that the nonmetal's nitrogen. We have to have oxygens in order for this to be polyatomic. Nitrogen is an outie, and since we have ic acid, that means that the nitrogen has 3 oxygens because outies want 3 oxygens in order to end with ic acid. Okay, number 4. Acid means hydrogen. Fluor means that fluorine is the nonmetal, and fluorine is an outie. Outies want 3 oxygens to end with ic acid, and since this ends with ic acid, that means there must be 3 oxygens attached to that fluorine. Okay, so hopefully you came up with that too. Alright, the second type of polyatomic compound that we could have is one where the first element is a metal and the second element is not a hydrogen. These names are going to end in ate or ite. The last time we did a compound, they were acids and they ended with ic or us. But these are not acids, these are salts. Okay? Remember, metals and nonmetals always create salts. We've had binary salts like NaCl, where there's just 2 elements. Well, now we're going to have polyatomic salts, where we have a metal functioning as a cation with a positive charge, and we're going to have a polyatomic anion with our negative charge. So the rule is, you say the name of the metal, then we're going to say the name of the polyatomic ion. Things that used to end with ic when it was an acid are now going to end with ate since it's a salt. And things that used to end with us when they were acids are going to end with ite now that they're salts. And then there will be a short list of things that you need to memorize. So let's see if we can do some examples of this. I'd like to look at our flowchart first. Okay, we're on the polyatomic side, and we're right here in this box where the first element is a metal with one oxidation state, and the second element is not hydrogen. Now remember, metals that have only one oxidation state are in group 1 or group 2 of the periodic table, and some can be found in group 3 like aluminum. The ones that have more than one oxidation state are those transition metals. We're not quite there yet. We're still right here. So the rule is say the name of the metal, then the name of the polyatomic ion. Things that used to be ic change to ate, and things that used to be us change to ite. And then I'll show you that list you're going to memorize here in just a minute. Now, how do we find the name of the polyatomic ion? That's this box right here, how to find the name of the polyatomic anion. In the last section we did acids, and now we're on this side doing the salt, and the any-outy rule is in the middle here, okay? So we want to know the name of the polyatomic anion. It's the same thing. If it has the number of oxygens the any and outy rule says it's supposed to have, then the ending changes to ate, so ic to ate. If it had one less, then the us that it used to have as an acid changes to ite as a salt. Two less, you have the hypo prefix and it stays ite. If you have one more oxygen, then the prefix changes to per and you have ate as your suffix. So let's look at some practice questions. These first three questions have metals that have only a single oxidation state, and so we should be able to name those. Alright, so the rule is that we say the name of the metal first. Okay, so the name of this metal is going to be sodium. Then we need to say the name of this polyatomic anion, PO4. So in order to do that, we're going to use our any-outy rule. Okay, so you'll see here that phosphorus is an any, and therefore it wants 4 oxygens. This phosphorus has 4 oxygens. The any-outy rule says if it has the number of oxygens that it's supposed to, then we end with 8, since we're talking about a salt. So we're going to say the stem of the nonmetal. Since we're back to a salt, the stem for phosphorus is phosp. And then, like the any-outy rule tells us, we end it with 8. Okay? So let's take a look at the second question here. We have another first element metal with only one oxidation state. So we're going to say the name of the metal, calcium. Now we need to say the name of this polyatomic anion here. We know that we're going to have to say the stem of the nonmetal for boron, which is going to be bor. And now we need to figure out what the ending is. We see that we have 3 oxygens attached to boron. Let's go see, is boron an any or an outy? Okay, boron is an outy, which means it wants 3 oxygens. If we have the number of oxygens we're supposed to from the any-outy rule, then we end with 8. Again, we do have the number of oxygens in the any-outy rule, so we'll end with 8. Alright, let's talk about where this 3 here comes from and where that 2 comes from. And I also probably should mention where that 3 comes from. You might have been wondering. Remember our saying for the charges on the polyatomic anions. POs, BOs, and ASOs are -3. So when we crisscross, you bring that 3 down. Now, sodium is a +1. And we would normally bring that down, but since it's a 1, it's understood and we don't have to write it. Okay, so let's talk about this one. Calcium is the cation here. Okay, and since it's in the second group of the periodic table, it's got a +2 charge. Now this BO3 here is our anion, and POs, BOs, and ASOs have a -3 charge. So this 3 here got crisscrossed down here, and now anytime that you're bringing a number other than 1 down onto a group of elements, you need to put those elements in parentheses and then bring the number down on the outside of the parentheses. The reason for that is because this number applies to everything in the parentheses. It's saying that we have 2 borons and that we are multiplying our oxygens by 2 as well. If you didn't put this in parentheses, then it would look like this. It would appear as though we have 32 oxygens, and that's not right. So remember, anytime that you're bringing a number larger than 1 down onto a group of elements, you put those elements in parentheses first and bring the number down on the outside of the parentheses. Okay, let's do this last one here for now. We're going to look at the first element. It is a metal that has only one oxidation state. So we're going to say the name of the first element, lithium. Now we need the name of this polyatomic anion here. So we're going to use our any-outie rule to do it. We see that sulfur is an any and wants 4 oxygens. This sulfur has 2 oxygens. Okay, so here's our any-outie rule. That sulfur had 2 oxygens, which is 2 less than what the any-outie rule says it's supposed to have. So we're going to have a prefix of hypo and then a suffix of ite. So let's put our prefix hypo in. Then we need the stem of our nonmetal, and since we're in a salt, it goes back to being sulf. And then we finish with ite. So we have lithium hyposulfite. Let me move that up just a bit. Okay? Now, these next 2 down here, we need to learn another rule for. But hopefully you have understood how we're coming up with the names for our first element metal with 1 oxidation state. Okay, let's see if we can figure out how to go from the name back to the formula. Let's try our first one here. We have barium pernitrate. Okay, so we have some information here. First off, we've started with a metal. Okay, so we can write down the atomic symbol for our metal, Ba. Alright, and now let's start breaking this part down over here. I see that we end with ATE, which means that this is a polyatomic compound. That means there's going to be at least 3 elements. We know one of them is barium, and all of our 3 compound formulas have oxygen. So I know the last element is going to be oxygen, and the middle element is going to be nitrogen because my stem here is nitre. So let's write down our N and our O. Alright, now we need to figure out how many oxygens do we give our nitrogen. Okay, what we need to know is nitrogen an any or an outie. We can see here nitrogen is an outie and it's supposed to have 3 oxygens. Okay, so if it had the number of oxygens it was supposed to have, it would just have 8. There would be no prefix. But we have pernitrate. That means that it must have 1 more oxygen than it's supposed to. So instead of 3, it's going to have 4. Okay, now the last thing we need to do is check our charges. Barium is our cation, and since it's in the second group of the periodic table, it's got a +2 charge. And the NO4 is our anion. It's not a POBO or ASO, it's not a SOCO or CRO, which means it's all the rest, so it's got a -1 charge. Since we have a number larger than 1 that's being brought down on a group of elements, we need to include parentheses around our polyatomic anion. Now we can bring the 2 down to the outside. The 1 from the NO is brought down here, but it's understood, so we don't have to write it. Okay, I want you to try and do the silver arsenite and the magnesium chlorate and see what you come up with. Okay, so here's what I've come up with. For silver arsenite, we write down the symbol for silver, which is Ag. Arsen is the prefix for arsenic, so we write down As, and then since we're ending in ITE, that's an ending that is for a polyatomic compound, so I know there's going to be oxygen. Arsenic is an Ni, which means it wants 4 oxygens, but that would give it an 8 ending. This has an ite ending, which means it's got 1 less oxygen than it's supposed to, so that's why it's got 3 here instead of 4. Silver, even though it's in the transition metals, only has 1 oxidation state, which is why we're able to name it like this. Pos, Bos, and ASOs have a -3 charge, so we bring that 3 down, and the 1 is brought down over here, but we don't have to write it because it's understood. Alright, the next one, magnesium chlorate. We write the symbol for magnesium first, Mg. Then chlor is the stem for chlorine, so we write Cl, and then ATE lets us know that this is a polyatomic compound, so it's going to have oxygens. Now we need to know how many oxygens. Chlorine is an Audi, and Audis want 3 oxygens to end with 8. This one does end with 8, and so that's letting us know it does have 3 oxygens. Magnesium is a metal in the second group, so it's got a +2 oxidation state. This is not a POBO or ASO. It's not a SOCO or CRO. That means it's all the rest, so it's got a -1 charge. So there's a 1 here that's understood, and we don't have to write it. And anytime we bring a number larger than 1 down on a group of elements, we put them in parentheses and bring the number down to the outside. Okay, so I hope that you got the same thing as I did there. Let's go back and get the rule for a metal that has more than 1 oxidation state. Okay, so here's an exception to the rule. Like I told you, there would always be. If we have a metal that has more than a single oxidation state, we get these 2 new rules. The reason we get 2 new rules is because 1 is for systematic and 1 is for common. Yes, those are coming back. So if we're doing the systematic version, you say the name of the metal, put the oxidation number in Roman numerals inside of parentheses. Then we're going to say the name of the polyatomic ion, and we'll use our Ni-Audi rule to help us do that. To do the common name, we're going to say the name of the metal ion. Remember, these are the elements that have common names, so we'll do the stem of their Latin name, and then Ich for the higher oxidation state, and Us for the lower, and then we'll finish up with the name of the polyatomic ion that we get from the Ni-Audi rule. Alright, let's do some practice after we take a look at our flowchart. Okay, so now we are right here. We're still on the polyatomic side, but now we're looking at first element metal with more than a single oxidation state, and the second element is still not hydrogen. So we have a systematic version and we have a common version. Okay, the same rules as what I just read to you. The name of the metal, Roman numeral of the oxidation state inside parentheses, and then the name of the polyatomic ion. These 4 asterisks are directing us towards our Ni-Audi box over here. Memorize the rest, we're almost there. The common name, we say the metal ion name. The 2 asterisks direct us to this box, so again, here's our list of elements, and there's the stem of their Latin names. Ich for the larger oxidation state, Us for the smaller, and then we say the name of the polyatomic ion that we get from our Ni-Audi rule. Alright, so let's try these last 2 questions here. Okay, so our new rule is say the name of the element if we're in the systematic version first. So we'll write iron. Then we need to get the oxidation state of this iron, so we can put it in parentheses using Roman numerals. Okay, so the way we're going to do that is by uncrisscrossing and reducing. So let's take a look at the oxidation states that iron can be. Alright, so iron can be a +2 or a +3. Now let's look over here at our ASO. Remember, Pos, Bos, and ASOs are -3. So there should be a 3 right here when we crisscross, but there isn't. There's a 1. Now, the only reason that there could be a 1 there is if we have the +3 version of iron. So if we had brought a 3 down on the outside of our ASO4 and a 3 down here, they would have canceled. So here's what that would look like. That means that this 3 and this 3 would cancel each other out. We could drop the parentheses and put them all together, which is what we ended up with right over here. So we have the 3 version of iron. So let's put 3 in Roman numerals right here. Now we just need the name of this polyatomic anion. We're going to use the any-outy rule to help us do that. So we'll go look at arsenic. Okay, so here's arsenic right here. It's an any, which means it wants 4 oxygens. We have 4 oxygens. So if you have the number of oxygens you're supposed to in the any-outy rule, then we end with 8. So we're going to say the stem of our nonmetal, which is arsen, and then we'll finish with 8. Okay? Now we need to do the common name. And to do that, we need the metal ion name for iron +3. So we're going to say the stem of the Latin name for iron, which is Fer. Then we need to decide if the ending is going to be ic or us. Remember, ic goes with the higher oxidation state and us goes with the lower one. So we have the ic version. And then all we have to do is say the name of the polyatomic anion, which we already found out right here. So we just bring that over, arsenate. Okay, see if you can do this last one here by yourself. I'll give you a hint. There is a systematic and a common name for this molecule. Okay, so here's what you should have come up with. Copper 2 bromite and cupric bromite. Let's walk through that real quick. For the systematic name, you say the name of the element first, copper. Then we need to decide what oxidation state it has, a +1 or a +2. Since we have a 2 on the outside of these parentheses, that must mean that we had the +2 version of copper. So we put Roman numeral 2 inside parentheses. Then we needed the name of the polyatomic anion. So we said the stem for bromine, which is brome, and then we needed to find out what the ending is. So we use the any-outy rule. We have 2 oxygens here. Bromine is an outy and wants 3 oxygens. So 2 is 1 less than 3, which changes the ending from 8 to ite. So we have copper 2 bromite. Then we need the common name. So we had to come up with the metal ion name for copper +2. So we're going to use the stem of the Latin name for copper, which is cupr, and then the larger oxidation state gets ic, so we have cupric. Then we simply bring over the same name of the polyatomic anion, bromite. So we have cupric bromite. Okay, now finally, the memorize the rest. I know you've been dying to hear about that. These list of polyatomic anions here, some of them follow our Post-Boson ASO's rule, and some of them not so much. So that means you're going to have to memorize those on your own. I'm going to try my best to offer you some tips and tricks with these to help you memorize them, but ultimately it's going to be up to you to do that, okay? Yes, you might have a quiz soon over it, and yes, that quiz will require that you know all of these and be able to use them. Okay, so here's those tips and tricks. You'll notice here that it's still a co, alright? There's a C and an O together, and we know that so's, co's, and crow's are -2. So it still follows that rule. You just have to realize that there's a C2O4, and then the name of it is oxalate. You need to know that. Here we have a really common polyatomic anion that comes up a lot called acetate. This is actually what vinegar is made out of. Alright, so acetic acid is vinegar. Notice what I just said there, acetic. I change the ate ending back into an ic ending, meaning that this is an acid again, okay? So these are polyatomic anions. That means they can be paired up with hydrogen, which will turn them all into acids, and so all of the ate endings will change into ic endings. Or I could pair them up with metals and they'll keep their ate endings because now they'll be part of a salt. Okay? So it's got a -1 charge because it's not a POBO, ASO, or SOCO or CRO. But you're going to have to know this formula, C2H3O2, or you might see it like this, where you have CH3COO. Alright? Either way you see it, you need to know the -1 charge, and you need to know that that's the acetate ion. Okay? Then we have thiocyanate. Okay, anytime you see thio, that's telling you that there's a sulfur there. And then CN, you remember as part of your exceptions, that's the cyanide, but here in this polyatomic molecule, it's cyanate, and it's got a -1 charge. Okay, then we have the chromate ion. So remember, Sos, Cos, and Cros are -2, so that gives you your charge. Then we have CrO4. Well, for us, we're going to say that anything that is not an outie is going to be considered an any. So even though chromium is a transition metal, it's not an outie. Therefore, we're going to make it like an honorary any. And any's want 4 oxygens. So we have 4 oxygens, and that lets us end with 8. So that one's pretty easy, chromate. The next one we have here is dichromate. So di means 2, so that kind of clues you in that there are 2 chromiums. You're going to have to just remember that there's 7 oxygens. And then again, Sos, Cos, and Cros are -2. That's still a Cro because it's chromium with oxygen. Then we have permanganate. Okay, we have a -1 charge on that because it's not a POBO or ASO or SOCO or CRO. That means it's all the rest. And then you're just going to have to know MnO4. I don't have any tricks for you on that one. Here we have peroxide. So we're going to have a -2 charge because oxygen is in the -2 column, and there are going to be 2 of them. Remember, we have the formula for hydrogen peroxide, which is H2O2. So if you've memorized that formula, the reason there's a 2 there is because of this -2 charge on the peroxide anion. So I don't know if that'll be helpful or not, but sometimes I find that useful. Okay, then we have the thiosulfate. Remember, thio is telling me that there's a sulfur here. Sos, Cos, and Cros are -2, and then you're going to have to just remember that there's 2 sulfurs and 3 oxygens in that molecule. Okay, then the last one is, I think, the funkiest of all. It is not a So, Co, or Cro, but it's got a -2 charge. Okay, you're going to have to memorize C4H4O6 and that's tartrate, and then it's got a -2 charge. That one, I don't have any tricks for you. Sorry. But these molecules here, these ions, do come up very often, and you'll need to be able to use them in any formulas, and you'll need to be able to take those formulas and turn them into names, or if you see it in a name, you need to be able to go back to a formula. So let's take a look and see if we can do that. Okay, let's see if we can turn these into their formulas. Potassium permanganate. Okay, so we're going to write the symbol for potassium, and then we need the permanganate ion, which we should have memorized. That's MnO4. Finally, we'll just check our charges. Potassium's in group 1, so it's got a +1 charge, and the MnO4 anion has a -1 charge. So they cancel each other out, and that gives us the final formula. Okay, let's look at number 2 here. Lithium thiosulfate. We're going to write the symbol for lithium, Li. Now we need the formula for thiosulfate. Now we just need to check charges. Lithium's in group 1, so it's got a +1 charge, and the thiosulfate ion has a -2 charge. So when we crisscross, we need to bring down a 2 in between Li and sulfur. Alright, now you see if you can do acetic acid and ferrous tartrate. Okay, I'm going to give you a few hints here. We are at ic and acid again, which means you start with a specific element. And then this is our common name here for a specific version of the iron cation. So make sure you figure out which oxidation state we're talking about there. Okay, so for acetic acid, acids always start with a hydrogen, and then we write down our acetate anion, CH3COO. Okay, sometimes you'll actually see this H at the end over here next to these double oxygens because the negative formal charge in that molecule is on this last oxygen, and the positive charge of that hydrogen pairs up with that negative charge there. But that's just extra information. I would definitely accept that answer. Okay. Then we have the ferrous tartrate. Ferrous is talking about the +2 version of iron. And let me move that up just a smidge for us. Okay. And then tartrate is C4H4O6. The charge on that is -2. Ferrous was +2, so they cancel each other out, and we don't have anything but our understood ones there. Alright, so hopefully you got that, and hopefully you would also be able to go from the formula to the name. The third type of polyatomic compound that we could run into is where the first element is a metal and the second element is hydrogen. The endings are still going to be ate and ite like they were before, and here's our new rule. We're going to say the name of the metal, then you're going to say hydrogen or dihydrogen. You'll use dihydrogen if there are 2 hydrogens present as the second element. And then we're going to say the name of the polyatomic ion. Remember, we use the any-outy rule to come up with that. We'll talk about the exception in just a minute. So here's some practice. Notice that each of these beginning elements is a metal, and that metal has only one oxidation state. You'll also notice that the second element in each of these is hydrogen. So we're going to be able to apply our new rule, which again is right over here. Name of the metal, then hydrogen or dihydrogen if 2 of them are present, and then the name of the polyatomic ion. Notice there's 4 asterisks. That's leading us to our any-outy rule box over here. Okay? So let's answer number 1. The first thing we do is say the name of the first element, sodium. Then we're going to say hydrogen or dihydrogen. In this case, there's only one, so we say hydrogen. And then we need the name of our polyatomic anion. So the chromium is going to be the nonmetal, so we're going to take the stem of that, and then we need to figure out what the ending is. Notice we have 3 oxygens here. Here we have our box that tells us what our innies and our outies are. You'll notice that chromium is nowhere to be found. But remember, I told you, anything that's not an outie, we're going to consider to be an innie. So chromium's an innie, which means it wants 4 oxygens. This chromium has 3 oxygens. Now, if it has the number of oxygens that it's supposed to have, it ends with 8. But this one has 1 less than what it's supposed to have, so it's going to end with ite. And so we have our final name, sodium hydrogen chromite. Alright, let's do the next one. We're going to say the name of the first element, which is calcium. Then we say hydrogen or dihydrogen. There are 2 hydrogens here, so we're going to say dihydrogen. Now we need the name of our polyatomic anion here. So we're going to use our any-outy rule to do that. We're going to say the stem of our nonmetal, which is going to be phosphate, because it's back in a salt. And then we need to pick the ending. So we have 4 oxygens. Let's go look at the any-outie rule. Phosphorus is an any and it wants 4 oxygens. And if it gets the number of oxygens that it's supposed to have, we finish with 8. So we have calcium dihydrogen phosphate. Alright, last one. We're going to start with the name of the metal, which is magnesium. Then we say hydrogen or dihydrogen. So in this case, we are back to hydrogen. And then we need the name of our polyatomic ion. So we say the stem for our nonmetal, which is phosphate. And then we use the any-outie rule. We have 4 oxygens here. And hopefully by now we're starting to figure out what's an any and what's an outie. You should remember phosphorus is an any, and any's want 4 oxygens, and this has 4 oxygens. And if it has what it's supposed to have, then we end with 8. Okay, let's see if we can go from the names to the formula now. We're going to just work backwards, alright? So we have barium as the first element, so we're going to write the symbol for barium. Then we have hydrogen, so we'll write the symbol for hydrogen. Then we have hypoarsenite. Okay, arsen is the stem for arsenic, so we're going to write the symbol for arsenic, and then we have an ITE ending, which means that's a polyatomic anion, so it's going to have oxygen. So we'll put oxygen there too. Okay, now let's deal with this hypo and ite ending using our any-outie rule. Alright, arsenic is an any, which means it wants 4 oxygens. Now we have a hypoite prefix and suffix. That means we have 2 less oxygens than what we're supposed to have. So arsenic is supposed to have 4, 2 less than 4 is 2. Okay, now all that's left is checking the charges. Barium is in the second group, which means it's got a +2 charge. Hydrogen has a +1 charge. And POs, BOs, and ASOs have a -3 charge. Okay, we're going to group the hydrogen's charge with the polyatomic anion's charge so that we get a net charge of -2. That means that the +2 here cancels with the -2 there, and we don't have to bring down any subscripts or parentheses. So this is the final answer. Alright, let's do the next one. Aluminum dihydrogen perborate. Okay, let's write the symbol for aluminum. Then we have dihydrogen, which means there's 2 of them. And then we have perborate. Bor is giving us the stem of boron, and then ATE is letting me know that this is a polyatomic anion, so there's got to be oxygens there too. So let's write the symbol for boron and oxygen. Now we need to figure out how many oxygens. We'll use the any-outie rule to do that. Okay, boron is right up here. It's an outie, which means it wants 3 oxygens. We have the prefix of per and the suffix of ate, which means we have 1 more oxygen than the any-outie rule calls for. So instead of 3 oxygens, we're going to have 4. Now we just need to check our charges. Aluminum has a +3 charge. Hydrogen has a +1 charge, but there's 2 of them, so that's +2. POs, BOs, and ASOs are -3. Now we're going to group the hydrogen and the polyatomic anions charged together. So we end up with a -1 charge for our polyatomic anion and a +3 charge here for the cation. So we need to crisscross and reduce. Anytime we bring a number larger than 1 down on a group of elements, we need to put them in parentheses first. Okay, so this is what our final molecule looks like. Alright, so hopefully you're able to work through either from the molecule to the name or the name back to the molecule. And then we have our exception as usual. What if the metal has more than a single oxidation state? Well, we go back to the same old, same old. You say the name of the metal, then we can do the Roman numerals in parentheses for the oxidation number. Then you say hydrogen or dihydrogen if there's two of them. And then we say the name of the polyatomic ion using our any-outie rule. That's, of course, for the systematic name. And then we can do a common name if the metal has a metal ion name. Everything else just stays the same. Okay, so here we have some formulas where each of the metals have more than one oxidation state. So let's name these really quickly because by this point we should be able to do that. Alright, we're going to say the systematic name and the common name if there is one. And it just so happens that I have chosen metals that do have common names so that we can get some more practice doing that. Okay? So the first thing we're going to do is systematic. That means we're going to say copper. Then we need to know what the oxidation state of copper is. It can be a +1 or a +2. Okay, so which version do we have? Well, you'll notice that we have a 2 down here. That came from copper when we crisscrossed. Hydrogen has a +1 charge, but there's two of them. And Pos, Bos, and ASOs are -3 charge. So if we combine the +2 and -3 charge, then we get a -1 charge. So that's why there is a 1 right here. It got crisscrossed from that one. Okay, so let's put the 2 in Roman numerals right here. Okay, then we're going to say hydrogen or dihydrogen, and we have two of them, so we're going to say dihydrogen. Then we need the name of our polyatomic anion. So we have boron here, so we're going to say the stem for that, which is bor. And then we need to decide what the ending is. This boron has 4 oxygens. Our any-outie rule shows that boron's an outie and wants 3 oxygens. If you have one more oxygen than you're supposed to, then you get a prefix of per, and your suffix is 8. So altogether, we have copper 2 dihydrogen perborate. Alright, now let's do the common name. For the common name, we need the metal ion name for copper +2. So we're going to say the stem of the Latin name for copper, which is Cooper. And then we need to decide what the ending is going to be, ic or us. Remember, it gets an ic ending if it's got the larger oxidation state, and an us ending if it's got the smaller. We have the larger one, so it's going to end with ic. And then everything else stays the same. So we're going to bring down dihydrogen, and we're going to bring down perborate. Okay? So I want you to see if you can do the second question and the third question on your own. Take your time, go back through your flow chart or through your notes, whichever one you've been using this time. Okay, let's go through these and see if you came up with what I came up with. Alright, for the systematic name, we said lead, the name of the metal. Then we needed the oxidation state for lead. It can be a 2 or a 4. This 4 here came from crisscrossing the lead, so we must have the 4 version of lead. Then we have 1 hydrogen, so we say hydrogen. And then we need the name of our polyatomic anion. Chromium is an Ni, so we're going to say the stem for chromium, which is chrome. Nis want 4 oxygens, and that's what this has, so it gets to end with 8. So we have lead 4 hydrogen chromate. Now we need the common name. The Latin stem for lead is plumb, and then since lead can be a 2 or a 4, and we have the 4 version, we end it with ic. So we have plumbic hydrogen chromate. Okay, question number 3. Iron is the name of the first element, so we write that down, and then we need to know what the oxidation state is. It can be a 2 or 3. Now this one's a bit tricky, so I'm going to write it all out for you. Okay, so iron can be +2 or +3, hydrogen's +1, and Pos, Bos, and ASOs are -3. So we're going to group the -3 and the -1 together, or excuse me, the minus 3 and the plus 1 together, and we get a minus 2. So there should be a 2 right down here in between the iron and the hydrogen, but there isn't. The only reason that there wouldn't be is if we have the plus 2 version of iron. That way, when we crisscrossed and brought the 2 down over here, it would cancel with the 2 that's supposed to be right there, which is exactly what happened. And they became 1s, and then those 1s are understood and are not written. Therefore, we have the plus 2 version of iron. So we write iron 2 and then hydrogen for 1 hydrogen. Then we have arsenic here, so we write the stem for arsenic, which is arsen. Arsenic is an any, which wants 4 oxygens. This one has 4 oxygens, so it gets to end with 8. So we have iron 2 hydrogen arsenate. Now we need the common name. Well, we're going to do the Latin stem for iron, which is Fer. And then we have the plus 2 version, which means we're going to end with us. So we have ferrous. Then we bring down hydrogen and arsenate. So we get ferrous hydrogen arsenate. Okay, now let's try doing the name to the formula. Okay, we have Stan, which is the Latin stem for 10. So let's write the atomic symbol for 10. Then we have dihydrogen, meaning there are 2 hydrogens there. Then we have arsen, which is the stem for arsenic. And we have ITE, which means that that's a polyatomic anion, so it has to have oxygens. So let's put the atomic symbol for arsenic and oxygen. Now we need to know how many oxygens. Well, hopefully you know by now that arsenic is an any, which means it wants 4 oxygens. And if it has 4 oxygens, it gets to end with 8. But this one we see ends with ite. If we end with ite, that means we have 1 less oxygen than what the any-outie rule says. So we need 3 oxygens here. Now we just need to check our charges. So 10 can be a plus 2 or a plus 4. Hydrogen is plus 1, but there's 2 of them. And POs, BOs, and ASOs are minus 3. Okay, so now we need to combine the plus 2 and the minus 3 together. Okay, so we have a minus 1 charge here. Now let's talk about this right here. We have stannus, which means that we have the lower oxidation state. So we have the plus 2 version of 10. That means that when we crisscross, we're bringing a 1 down here, which is understood. And then anytime we bring a number larger than 1 down on a group of elements, we need to put them in parentheses first. And so we end up with this formula here. Okay, now let's do this last one. This one I've thrown in one of those polyatomic anions that you're supposed to memorize, so be aware of that. First thing we're going to do is write the symbol for nickel. Then we have hydrogen, so let's write the symbol for that. And then we have the thiosulfate ion, so let's write that down. Okay, now we just need to check our charges. Nickel, we have the plus 3 version. Hydrogen is a plus 1. And the thiosulfate ion is a minus 2. We're going to group the minus 2 and the plus 1 together to get minus 1. Okay, so the 1 would crisscross down here, and then the 3 would need to be brought out here. Again, anytime you have a number larger than 1 being brought down on a group of elements, you need to put them in parentheses first. Alright, so there's our final molecule. Alright, we are finally coming to the end. Okay, so we have just 2 more exceptions to go. If the polyatomic ion is a SO or a CO, then we name the compound a different way. You're going to say the name of the metal, and then instead of saying hydrogen, you're going to say bi, and then you'll put the name of the polyatomic ion. So an example would be something like this. We have a first element metal. That metal has 1 oxidation state, sodium's a plus 1. Then we have hydrogen, and then we have SO3. Okay, so normally, according to our previous rules, we would have said sodium, hydrogen, sulfite, because sulfur is an any and it wants 4 oxygens, but this one has 3, so instead of ending with 8, it ends with "ite." But instead of saying sodium hydrogen sulfite, we're going to use our new rule because we have a "so" right here. So we're going to say bi, and that's going to take the place of the word hydrogen. So we'll say sodium bisulfite. And I've just noticed a typo here in the notes. Those are not eights, those are ites. So go ahead and make that change, please. Alright, let's do some practice. Okay, so we only have 2 practice questions here. The first one is what we just talked about. It's a first element metal with 1 oxidation state. There's a hydrogen as the second element, and it's got a Co as part of the polyatomic anion. So let's come up with the name for this. We're going to say the name of the element, which is lithium. Then, instead of saying hydrogen, we're going to say bi, because this hydrogen is paired up with a "so" or a "co." And then we need the name of this polyatomic anion. So we're going to have the stem of the nonmetal, except carbon is going to say its full name here. Now we need to know how to finish that. We have 3 oxygens. Carbon is an outie, which means it wants 3 oxygens. So if it has what it's supposed to have, then we end with 8. So we have lithium bicarbonate. Okay, let's see if we can go from a name back to a formula. So here we have rubidium, so let's put the symbol for that. Then we have a bi here. That indicates there's a hydrogen. And then we have sulf, which tells me there's a sulfur, and there's an ATE at the end, which means this is a polyatomic anion, so there must be oxygen. So let's put the symbol for sulfur and oxygen there. Now we need to know how many oxygens. Sulfur is an any, and it wants 4 oxygens. If it has 4 oxygens, then it gets to end with ATE, which is what it does end with. So that means there must be 4 oxygens here. Now let's check our charges. Rubidium has a +1 charge, hydrogen has a +1 charge, and So's, Co's, and Crow's have a -2 charge. We will combine the -2 charge and the +1 charge to get a -1 charge. So we're going to bring that one down here and the rubidium's one down here. They're understood, so we don't have to write anything. That means this is the final formula. Alright, so we're at the last exception. If there's a metal that has more than a single oxidation state, then we will have a systematic way of naming it and a common way of naming it, just like always. So here we have a metal with more than 1 oxidation state. Hydrogen is the second element, and it's paired with a "so" or a "co." So let's name that. We'll start by writing the name of the first element. Then we need to have the oxidation state of the first element in Roman numerals inside of parentheses. So this 2 here comes from the nickel. Remember, nickel can be a +2 or a +3. Then we have a hydrogen here. Normally we would write hydrogen, but since it's paired with a "so" or a "co", we're just going to write bi. Now we need the name of the polyatomic anion. So we're going to write the stem of the nonmetal, but since it's carbon, we're going to say the full name. And now we need to know how to end it. Carbon is an outie, which means it wants 3 oxygens to end with 8. This has 4 oxygens. So if you have one more than what you're supposed to, then you get a prefix of "per" and a suffix of 8. So we get nickel 2 bipercarbonate. Now, I'm not saying that this molecule actually exists. In fact, I'm pretty sure it really doesn't. But we're going to use it just so that we can have practice on the naming. Now, nickel is not one of the elements that has a metal ion name, so we can't come up with a common name for this molecule. but we've had so much practice with it so far, I really don't think we need to. I could have switched it out and had iron or copper or tin or lead, and then we would have a common name. But I think you got it. Now let's see if we can go from the name to the formula. So the first thing we have here is cobalt, so let's write the symbol for cobalt. Then we have bi. That tells us there's a hydrogen there. Then we have carbon and ITE. The ITE lets me know that there's a polyatomic anion, which means it must have oxygen. So let's put the symbol for carbon and oxygen. Now we need to know how many oxygens. Well, we ended with ITE. Carbon is an outie, which means it wants 3 oxygens to end with 8. But here, you see we're ending with ite, which means we must have 1 less oxygen than we're supposed to. So instead of 3 oxygens, we're going to have 2 oxygens. Now we're going to check our charges. We have the +2 version of cobalt. Hydrogen is a +1, and so's, co's, and crow's are -2. So we're going to group the -2 and the +1 together. So we get a -1 up here. When we crisscross and reduce, we're going to bring a 1 down here between cobalt and hydrogen, which we don't have to write because it's understood. Now the +2 here, we will have to bring down. But remember, anytime you bring a number larger than 1 down to a group of elements, you have to put them in parentheses first. So here's our final molecule. Alright, and that's it. That's all of the polyatomic compounds that you could possibly run into and how to name them. So you can do it for any polyatomic compound in the whole world now. If you have any questions, please come see me for tutorials. Make sure that you keep practicing these so that you can do them off the top of your head. They'll become second nature to you. And as always, thank you for learning with me today. Bye.